Resume recording. Okay, today is this February 13, 2023, and we're going to continue with the material that we started last week. Last time we just covered electric charge, electric force, and here you go. Not just electric charge and electric force, but quantization of charge as well, charge and electric force. That's what we covered. And this time I'm going to cover an electric field. But let's, before we go into the electric field, let's do a little bit of an example here, right? And so you can become familiar with the idea of electric force. Okay. Here you go. So here you saw those illustrations here, right? Showing the free body diagram. First, the free body diagram in the charge number 1, and then the free body diagram in charge number 2. And here is the two charges being subjected to the force, the action-reaction pair. Action-reaction pair. Remember, recall what we saw in mechanics, right? In mechanics, Newton formulated that third law of mechanics. Whenever two objects interact with one another, the force between them is equal in magnitude and opposite in direction. Okay, that third law of motion also applies to electric charge. It applies to the microscopic world. And it's amazing that something that was formulated before electricity became a formal science, it still applies to this new science and even quantum mechanics, okay? So it's amazing that we formulate a theory like 3 centuries before some new discovery, and that theory that was formulated 3 centuries before is still applied to the new discovery. So that's the power of a successful theory. It resists, time. It remains valid even as time goes by. Okay, here is the force between two charges of like signs, right? And here is the F sub ij. Here's what that means, right? Force of charge I applied to charge J, right? Let's put that apply it to charge J. Let's write that down this way. And here we go. We have those two charges. I mentioned that to you before, how we can write this force in a vectorial notation, whether it's vector position from 1 to 2 or vector position from 2 to 1. The vectorial formula for the Coulomb force also applies. Okay, so here we go. Now, what about if we have 3 charges, right? That would be one example a little bit more complicated. Let's say, suppose that we have 3 charges lining up in a straight line, okay? And what we want to do, we want to find out the net force on charge number 1. That's what we want to do. So here you go. Let's play the movie again. We have those 2 charges, those 2 initial charges. Okay. And I want to know the force in 1 due to charge number 2. Okay. And we have this force that should already be familiar with. It's going to be an attractive force. F of 2 in 1. F of charge 2 applied to charge, force of charge 2 applied to charge 1. Right? If we place a third charge further away, those forces are going to sum up vectorially, exactly in the same way that we did in mechanics. So we have this vector position from 1 to 3. And because the 2 charges has the same sign, we are going to have a repulsive force. Because this charge is further away than from this charge, the distance from 1 to 3 is larger than the distance from 1 to 2, it's reasonable to assume that the force of the charge 3 in 1 is going to be smaller. It's going to have a less intensity. Okay, it's reasonable. Doesn't mean that's going to be correct. Okay, strictly, and then the net force is going to be something like that. The net force in 1 is going to be something like that. Okay, we can spell that out in equations. Let's go back to our, here you go, electric force. We're still doing electric force here. Very soon we're going to do the electric field. Okay, so example. Example of Coulomb's law. Consider 3 charges distributed along the x-axis, right? From the left to the right, we have a positive Q1 charge greater than 0. Q2, that's going to be going back to our illustration. It's going to be negative. So the negative sign is already implicit in the value of the charge Q2. And Q3 greater than 0. Okay. There, the distances from 2 to 1 and 3 to 1 are respectively. Here we go. R12 and R13. So find the net force applied to charge 1. Okay. And I'm going to abbreviate that as charge 1 F net 1, like that. Magnitude and direction, by the way. Magnitude and direction. I have already solved part of this problem, right? It's going to be the easiest type of superposition of force problem that you're going to find. Okay. So let's start with my formulas here. Here you go. Solution. And I'm going to do something else too. Yeah, in addition to this axis, to this vector position here, I'm going to also label this as the x-axis. I'm going to make it thicker so you can understand that there is a difference, right, between those two lines. Here's the x-axis, here's the vector position from 1 to 3. Okay. I'm going to place it in the other slides as well. Okay. Again, Q1, Q2, vector position from 1 to 2. That's an attractive force. Q3, vector position from 1 to 3. And that's going to be the force that 3 is going to apply to in 1, the charge 1. Charge 3 is going to apply to charge 1. Okay. That would be our guess of the net force. Okay. It doesn't have to be necessarily something like that, okay? Whether this force here is greater, the magnitude is greater than that, doesn't depend only on the vector position. It also depends on the value of the charge Q3, right? So yeah, I'm just assuming that F31 is less than F21. The direction of the force is straightforward, right? It definitely cannot be the direction of this this force here has to be repulsive because those two charges. The only question is what's going to be the magnitude. We do not know the magnitude unless we have actual numbers. But let us assume that the magnitude of this force is less than the magnitude of this one. So if that's the net force, so what do we write? Let's go there, back to my, here you go. Force of, I'm going to write down in terms of force of 2 in 1, right? Force of 2 applied to 1. I'm going to write that down in vectorial way. So it's going to be Q1, Q2 divided by R12. By the way, not just R12, it's R12 square. I prefer, most books prefer to put the K outside the ratio, and we still have to put our unit vector R from 1 to 2. And then we have to sum with the other one. The nice thing about the software is that I don't have to keep on typing everything from scratch, right? I can just copy and paste. I can just copy it and paste and change a little bit here and there. So that would be the first step in solving your problem. In the next step, you're going to recognize that those vectors, those unit vectors R12 and R13, they are equal to each other. Because, here you go, R12 is pointing to the right, R13 is pointing to the right as well. So their unit vectors are also going to point to the right. It happens that their unit vectors are going to coincide with the unit vector in the x direction. So that's something you can recognize rather easily. I can even, let's see here, make another drawing. Okay. Of the unit vectors now. This unit vector here most likely is going to be shorter than the original vector R12. And let's see if I can. Yeah, good. And let me fix that. I don't want that other arrow there. Yeah, here you go. Now I have it. Unit vector means magnitude 1. And we can have the same for the unit vector 1, 3. Move a little bit higher. Here should be R13. Okay. Make it a little bit closer, right? Here you go. And let's write it down. And R12 is equal to R hat 12 is equal to R hat 13, which is going to be equal to X hat as well. Here you go. I'm going to even put the X hat right in here. Their magnitude is 1 because those are unit vectors. Like that. And I want to, because those are unit vectors, I'm going to make them a little bit larger, to a little bit thicker as well, to distinguish from, like that. Here you go, from the vector position. So now we can go the next step. And the next step should be write down that R12 is equal to R13, which is equal to X hat. Like that. When we do that, we can place those right here. We can replace R12 and R13 hat. And we start to get a simpler equation. Right? So I'm going to put KQ1 in evidence. And I'm also going to put X hat in evidence because those are common factors. Take out this X hat. I don't need this Q1. I don't need the K because it's already a common factor. And that should be the final answer. But wait a minute. We can do something else too. Okay? We can do something else too. What else can we do? We know that Q2 is positive, right? Here you go. No, Q2 is negative. Sorry, not positive, but negative. Yeah. So we can here write it in a different way. And we can write that in terms of the modulus. Okay. And when we do something like that, because Q2 is negative, you know, we have to put a negative here outside. Q3 is positive, right? Q3 is positive, and then we can do the same as Q3. But because it's positive, we don't change the sign here of the equation. That's one thing that we can do, just to point out that one of the forces is pointed. Wait a minute. Let's see. There is something wrong here. Let's see. Let me see what's going on. R12. R12. Let's see. Okay. So I made a mistake here, right? So what the mistake I made here? I switched it. Let's see. Yeah, no, it's not a mistake. It's still correct. Okay, it's still correct. From 1 to 2, yeah, and from 1 to 3 is gonna be positive. Okay, it's just a matter of notation here. It's just a matter of notation. Okay, so yes, there is the only mistake. Yeah, there is a mistake here. This notation here must be repeated here. Okay, here you go. That was the mistake that I made. From 2 to 1, so because from 2 to 1, we must have a negative X hat. Here you go. Now we have it right. This one is going to be minus, and this one is going to be minus. Okay. And now, oops, that's not R21, that's 3-1. Okay. 3-1. That should be 3-1 as well. From 1 to 3. Okay, here you go. Sorry. 1 to 2 and 1 to 3. Let's do it this way. That's easier. That's better. Okay. Oh gosh, peraí. No. 2 to 1, 2 to 1, 2 to 3. That's right. That's right. This way. 3 to 1, 2 to 1, 3 to 1. Here you go. That's the right notation, right? I had written down incorrectly. So that should be 2 1 here. That should be 3 1 here. Okay. If 1 to 2, why is that? From 1 to 2 is positive, but from 2 to 1 is going to be negative. That's the little boo-boo here that we have. Okay, and now we have it in the right way. We have here this negative. That's going to be 2 1 here and 3 1 here. And now we have it right. 3 1 2 1. Okay, and then finally, I'm gonna cancel the sign here. This one is going to be positive. This one is going to become negative. Right? Okay, now we have it right. The force due to charge 3 is going to be along the negative axis because it's a repulsive force. And the force due to charge 2 is going to be along the positive x-axis because it's a attractive force. Okay. The net force, that shouldn't be, let's see, that should be like that. Let me elaborate a little bit more. Okay. The correct way is 3 in 1, right? And here you go. I want to find the net force applied to 1. Here you go. That would be the right way, right? And then here you go. I'll fix that as well. Good. That's force of 2 in 1. That's force of 3 in 1. Okay, that's one type of problem that I'm going to see. And then you can substitute numerical values depending on the problem that you have. You can put numerical values in there to get the correct numerical result for this force, right? Okay, so let's summarize. Let's recap, right? So here you go. Let's start right here. We have this positive charge that's sitting down next to the negative charge. Okay. There is a vector position that goes from 1 to 2, but there is also another vector position that goes from 2 to 1. Okay, that's where we got into trouble here. Here you go. I'm gonna change the format shape. Yeah, and then this one. Nope, not this one. And arrow. This one here, this one. Yeah, and then we also have this other vector position that goes from the charge 2 to charge 1, which, by the way, is going to be minus this one because they're pointing in opposite direction, although they have the same magnitude, okay? So we end up having this force that's going to be attractive, contrary to this guy here, because the sign of this charge is negative. Okay. And then we put we have a third charge in here that's going with a vector position from from 1 to 3. That's R13. But we also have the other vector position, right? That goes from 3 to 1. That points in the opposite direction. Good. And this one, good. 3 to 1 that points in the opposite direction. Okay. Which is producing this force that is repulsive. Because this charge is positive, the resulting force is going to have the same direction as this other vector position. Because this charge is negative, right? Because this charge is negative. Let's get the other one. Here we go. Right in here. Because this charge is negative, this force here is going to have a direction opposite to this vector position. And then we finally have this net force right here. There is one more type of problem that you want, that you're going to be exposed to. What you saw here is a one-dimensional problem. Let's write it down. This is an example. This is a 1D example. We also have, this is a 1D example. We also have a 2D example. 2D example. Let's take a look at our 2D example. We have our x-axis with the origin. We have a y-axis. They both have the origin there where they are crossing. We're going to put a positive charge Q1 at the origin of the xy axis. A Q2 at distance A along the x-axis. And a Q3 now it lies along the y-axis. That's why I call that a two-dimensional problem, right? Because the charges now are no longer aligned. They are no longer along a single direction. So just like before, we want to find out what is the net force. Apply it to charge 1. Okay, so here you go. Charge 3 is going to apply a repulsive force on charge 1, which is going to be along the minus y hat direction. Charge Q, let me do it better here. Let me fix this one, hang in there. Take this one out. Charge 2 will have an attractive force. Again, I'm using the notation of force of 3 applied to 1, force of 2 applied in 1. Right? And let's not forget, the vector from here to here is going to be R12, right? And from here to there is going to be R21. Let's not fall into this mistake again. And then we end up having this net force. Let's see here what yeah, okay. Yeah, let's do this way, right? This guy should be the force should be at the center of the charge. I didn't want to put at the center of the charge because it may be covering the sign, right? Okay, now we have it. Here's going to be the net force applied to charge number 1. That's how we solve this problem in a qualitative fashion. And then we have this angle theta. Okay, So consider going back to our problem. We also have a 2D problem, okay? Consider three charges, Q1, Q2, and Q3. Q1, Q2, and Q3. Let's make sure the signs are correct. Yeah, negative. Q2 is negative, Q3 is positive, Q1 and Q3 are positive. Three charges. Okay. The first charge is located at the origin of the XY axis. The second charge is at A0, right? X equal to A, Y equal to 0. And the third charge is at 0B. 0B. Find the magnitude of the net force. Magnitude of the net force. Apply it to 1. And its angle with the x-axis. Angle theta. And its angle theta with the x-axis. Oops. Symbol. What's going on here? Ah. No symbol again. Here you go. Now it should be right. In terms of the given parameters. In terms of the given parameters. So let's go for the solution again. We're going to use the same formula that we used before. It's the same notation as well. Here you go. F1 net is F21 and F31. And we're not going to make the same mistake we did before, right? So here you go. I'm going to put an equal sign here. F21 is going to be KQ1, Q2, R hat 21 divided by R21 square. And KQ1, Q3, R hat 31, R31 square. Okay. That's what we have. Okay, next step. What is the distance between charge 1 and 2? Going back to the drawing. The distance is A. So R21 is going to be replaced by A. And R31 is going to be replaced by B. That's the distance. Okay. And what else? Okay, now we have to translate those unit vectors in terms of x hat and y hat. Okay. R from 2 to 1 is going to be to the left. From 2 to 1 is going to be to the left, going to be minus x hat. Okay. So here you go. Minus x hat. Remember, from 2 to 1, pointing to the left. And from 3 to 1 points downwards. So it's going to be minus r hat, y hat. Minus y hat. Okay, let's clean that up. Here we go. We are going to put a negative sign here. We don't need that negative anymore in the parentheses, and I'm going to put this negative sign here as well, right? And don't need that parentheses anymore. Just like before, let's factor everything that we can, right? But now we do not have the same direction, unit vector direction. So the unit vector must remain within the parentheses. And then we can do that little trick of ours again. We know that Q2 is negative. It's always, oftentimes it's important that you do something like that to visualize better the problem. Because Q2 is negative, I can here write it like that. Because Q3 is positive, we can here write that without changing the sign. And there is one more step that we have to make to come up with. We can cancel out this negative sign by inverting those signs right here. Let's see if it makes sense. Always check the illustration of your problem, right? So this equation here, this result here is telling us, I didn't get the final result yet, okay? We are just checking if everything is right. This result here is telling us that the force due to charge number 2 is along the positive x-axis. Is it along the positive x-axis? Yes, it's pointing to the right. This equation here for charge number 3 is telling us that the force of 3 applied to 1 is along the negative y-axis. Does it says that it looks like it's along the negative y-axis? Yeah, it is, it says. So you are not done yet. That's the vectorial result for the net force. Now we're going to write the magnitude of the above force. Okay, so those two vectors are perpendicular to each other. Because those two vectors are perpendicular to each other, what we have to do? We have to come up with a square root right here, right? We have to square the first term. Here you go. We eliminate the x hat because we are just trying to find out the magnitude. And by the way, I gotta write that down here, magnitude. Magnitude, this one right here, right? We cannot have a vector equal to a scalar, right? And we do the same here. Okay, here you go. We are going to square this term. And when I square this term, I have to add a positive sign here, and we eliminate the y hat. I can go one more step to simplify my equation. And this step is by eliminating this negative sign, because when we square a negative sign, the negative sign becomes a positive sign, right? We can go one more step, right? I'll do, here you go. What the next step we can do? We can distribute the squares to each of those terms, both determine the x direction. I start with the wrong one, but that's okay. Here you go. Square here, square here. Okay, and here you go. We got our final result. There is nothing else we can do here. There's nothing else we need to do here for this, for the magnitude of the force. Now we have to find the direction. Now we have to find the theta angle. Okay? Theta angle. Let's take a look at our drawing. Here you go back to our drawing. Very important to draw, to make a drawing of your physical situation. Same thing as mechanics, right? Mechanics, we're doing drawings all the time to solve problems. Drawings are very important because it helps you visualize the problem. And not only helps you visualize the problem, but it cuts down the amount of work that you have to do. Okay, remember that old saying, picture is worth 1,000 words. That's what we have here. Okay, that's what we have here. The angle theta is downwards, right in here. Let's see what's my next. Okay, so I'm going to make another drawing here. Here you go. But now I'm going to just emphasize the charge 1. Okay, I will still keep it in the x-axis, in the y-axis, but I want to emphasize the fact. I'm going to make a little bit longer those axes, right? So you can start visualizing F21. Remember, this is my free body diagram. It's going to be something like that. Let's see if I can get it. I'm going to, here you go. Get this guy right in here. And I'm going to eliminate the arrowhead. Good. Same length as this one. And we must have also the same length here. Here you go. My net vector is a little bit off, right? Did you notice that? My net vector became a little bit off because I didn't do what I'm doing right now. I didn't do before what I'm doing right now. Here you go. And then I'm going to eliminate the arrow as well. Okay, so here you go. So my net force is going to be a little bit downwards. The theta angle is like that. So this theta angle, the tangent of this theta angle is going to be this side divided by this side. Right? Let me save it. From the illustration. From the illustration. From the PowerPoint illustration. We have a right angle triangle. We have a right angle triangle with an angle theta given by, here you go. I'm going to save this guy here because I'm going to need it. Tangent. Your tangent of theta is equal to, going back here, F31, magnitude of F31 divided by magnitude of F21. Magnitude of F31 divided by magnitude of F21. Here. Okay, so here you go. Magnitude of F31 is part of this equation here, not everything, okay? You could also have done in terms of sines and cosines, right? If you wanted. Here you go. F31 is this one here, right? 3 and 1, right? F21 is going to be the other term. It's going to be the other term. Here you go. Hey, Isn't that nice? We're going to have some simplification here. Can you see the simplifications there? The square root is going to disappear, right? But before the square root disappear, we see that this term here also disappeared. Okay? So let me take out this square root from the parentheses first, and then we proceed with the simplification. Now, what is upstairs is going to become something like that, right? And what is downstairs is going to become something like that. Can you simplify further? Doesn't look like. All we can do is to rearrange this equation to put it in a more familiar fashion. A goes upstairs, right? And here you go. And that's my final result. Two examples using Coulomb's law. 940. And then you can have other problems that are more difficult, okay? So that first problem that you saw with the charge in a linear fashion, distributed in a linear fashion, is the simplest type of problem that you're going to find involving three charges. Okay, this one that we saw right now, again, is the second simplest type of problem involving three charges. Okay, the next level of difficulty, I'm not gonna solve that. The next level of difficulty involves a problem that you do not have. You do not have a right angle triangle, but let's say you have something like that. You know, that will be the next level of difficulty. This position here would be like a divided by 2, right? In this specific case, I'm going to just show you in a qualitative fashion how this problem would be solved. Should be, you know, a vector connecting the first charge, the third charge to the first one, right? Here you go. Oops. Would be something like that. And now my net force is going to be a little bit more difficult to calculate because it doesn't involve right angle triangles, right? It involves some more complicated configuration. Because that would be my new result. Here you go, net force. Good, and then I have to remove here and here net force. And I am going to emphasize. Yeah, you know what? It's the same color, right? It doesn't fit there. But that's what I mean. Here, this one is going to be F3-1, the other one F2-1. Okay? I'm not going to do that, but just for you to have an idea. Okay, so what time is that? 8:43. Let's take attendance. Any questions before we move forward? What I want to do, I want to take attendance first, and unless you have questions, I'm going to stop recording momentarily, pause the recording, remind me to turn on start. Let's see, Janet is here, right? Janet Garcia, is that right? Okay, and it looks like we have more students coming in. Noor, are you there? Noor Hassan?
Yeah, I'm here.
Okay.
I just had some trouble reconnecting.
Okay, anybody else? 21, 20. Okay, we're in good shape. Good. Now, what we are going to do now, we are going to talk about the electric field. Remember? Here you go. Let's go back here to the topics. So we start with the electric charge. The electric charge is an abstract concept that was created to understand the electrical phenomenon. It's just like mass. Mass also is an abstract concept. It's an idea that we have created to explain the world, right? And electric charge too. What else do we have to know about this chapter? We have to know about the quantization of charge as well. Charge objects are charged according to an integer number of the charge of the electron, right? That's 1e. In nature, you're going to just find out object that has charges like 1e, 2e, 3e, and here you go, ne. That was the experimental result obtained by Robert Millikan. We talked about electric force, which is our first electromagnetic law, Coulomb's law. Coulomb's law. And now we're going to talk about something that's also very abstract. You see, we're going to start talking about something that's called the electric field. Okay? And the best way to visualize the electric field is in terms of the electric force. That's the best way to visualize the electric field. It's let me write that down. The electric field is an invisible quantity related to the electric force. So in order for you to understand the electric field, you have to understand the electric force. So let me give you a qualitative idea of what the electric field is all about. We start here with my electric charge. Okay. Let's I usually like to play the movie just like I always do, right? Start from the simplest object there in our drawing, and then we then draw the x-axis, right? Playing the movie. Charge, x-axis, next will be the y-axis. And then we visualize, and then we think about what would happen if I put another charge there in the xy space, okay? You already know that there will be a repulsive force between those two charges. In that specific charge, the force is going to be away from Q1. Okay, now what I'm going to do, I'm going to remove this charge. Okay, this charge here we call a test charge. The second charge here, we call it a test charge. I'm going to remove this charge, and you already know the moment I remove this charge, there is no force there anymore at that spot. Okay. However, even though there is no force, electric force at that spot, because there is no charge whatsoever, something else is left behind. Something else is left behind. This little arrow here, that red arrow that you see, is what we call the electric field. Okay? And the electric field, the direction of the electric field is always dictated by this test charge that will always be positive. Okay, so we have this test charge at that position. We can come up and put another charge here, another test charge somewhere else, and then we start mapping the electric field distribution of my charge Q1. Okay, we have again a repulsive force in that other test charge, and when we remove the test charge, the force ceases to exist, but what's left behind is the electric field again. Okay, and then you can populate the XY plane with the electric field arrows, the electric field vectors, by placing test charges that are always positive. Here you go. Here is the direction of the electric field at each of those spots. Okay, that's what the electric field is all about. Let's see what's the other. If we get closer and closer to my main charge, the electric field is going to increase in intensity because it's closer to the source. Similarly, if you have put a test charge here, the force here would be stronger than the force here, right? And so is the electric field as well. Okay, so let's write that down. What we just discussed here. An invisible quantity related to the electric force. That's what the electric field is. And it's sometimes very difficult to visualize. It's difficult to visualize because it's a very abstract concept. Okay, so I like to define the electric field as the electric field. The electric field can be thought as the ability of a charge to exert, I'm going to call it a main charge, to exert a force in a given point in space. Okay, even though you don't have anything, you may not have anything at that spot, you are not going to have a force at the spot, but you are going to have a electric field, which is going to be the ability of a main charge to exert a force at that given point in space. The mechanical analogous of the electric field, okay, is the acceleration of gravity that we also call the gravitational field. Okay, the gravitational field. So that little g vector that you see, that we draw, right, in physics, in mechanics, in physics 7, in physics 6, is a gravitational field. So here you go. I'm gonna mechanical analogous, right? Yes. Now we're gonna draw something different here. There is no force being exerted at that spot because there is no gravitational force exerted at that spot because you don't have any mass whatsoever there. But you still have the ability to exert a gravitational force because we have the acceleration of gravity there. Go. Good. So, oops. I don't want to be here. Gonna move a little bit to the left, okay? And then we can go ahead and label those vectors G arrow at the top. I'm gonna make it black, but instead of E, I write that down, the little G, like that, acceleration of gravity. That's the mechanical analogous of the electric field. Okay, so here we go. Looking better now. Okay, so what's the definition of this electric field? Right, just remember from physics 6. Just remember from physics 6. Yeah. The weight, right? Same thing here. The weight is equal, right? Don't forget that the weight is a force, is equal to mg. mg is a vector. Oh, is a vector. I'm going to emphasize that the weight is a force, but I'm going to even emphasize that is the gravitational force. I'm putting a G there, subscript. From this equation, you see that the acceleration of gravity is equal to what? To the gravitational force divided by a mass of an object. Okay? Well, we have something similar for the electric field. The electric field, okay, so here you go. Note that the gravitational acceleration or the gravitational field is equal to the force, to the gravitational force, divided by the mass of the object, which by the way, is the source of gravitational force, okay? Which, by the way, this concept itself is the source of gravitational force. I'm not saying that the little mass is the source of a gravitational field. No. The source of the gravitational force is that larger mass, the Earth, right? The Earth's mass itself. In the case of the electric field, we have something similar. Or, you know, the electric force. Let's go back to the electric force. Okay, I'm gonna get this. So we're gonna, let me get everything here. Now I'm going to define, you know, force between a test charge and between a main charge. I want to put that like that. Main charge and a test charge. You know what? I'm gonna put like that. 1 and 2. 1 and 2. Force of 1 applied to 2. Okay. Force of 1 applied to 2. Let's go back to this drawing right in here. This one, my charge 1. And let's say this one here is my charge 2, my test charge 2. Even better, instead of 2, I'm gonna put T for test charge. And I'm gonna change my notation for 1T, okay? 1T is gonna be what? Force of 1 applied to the charge T is gonna be, charge 1, charge T for test, okay? Divided by R1T squared. Okay, and that should be R1T hat. Like that. Where T refers to the test charge. Okay. QT. Going back here. Okay. That's R1T is gonna be what? R1T. Let's get this. Here we go. It's gonna be the vector that goes from the main charge 1 to the test charge QT. And let's see if I can get my vector position that I had before. Yeah, here you go. Yep, right in here. Vector position from charge 1 to test charge T. And then what I have to do here, I have to label that force. Here is going to be electric force F1T, like that. I'm going to shorten a little bit more this vector so you can see its arrow. Right? Here you go. Oh, gosh. Oh. Oh, yeah. What happened here? Let's see if I can get it now. Good. Okay. So going back to my drawing here. Here you go. So what do we do? The electric field, mathematically, I already gave you a conceptual idea of the electric field. Now I'm going to give you a mathematical definition, right, of the electric field. Mathematically, the electric field is given by the force divided by the test charge. Okay. And this force divided by the test charge becomes the electric field of the main charge 1. And we do not need to write the test charge anymore. Okay. And now my vector position is going to be a vector position from the main charge 1, anywhere in space. to simplify its notation. Simplify the notation, we write down that the electric field of a point charge is just the whoa, good. Without we write that down without the subscript. That's just a simplification. Yeah. Oh, don't need that R, okay? KQ1 divided by R squared. Mathematically, that's how you write it. So it's the force divided by the test charge, whereas right here is the force divided by the test mass, right? You can call that the test mass. So one way to illustrate those electric fields is by drawing electric field lines in space in the radial direction. Okay, notice that I changed the color, right? Why did I change the color? Let's see. I changed the color because the black color is for force and the red color is for the electric field. That's why, okay? So here we have a force in black, and then we have the electric field in red, okay? Black and red, and so on. Here you go. One way to represent the electric field is by vectors. At every point in space, you draw a vectorial symbol. You draw an arrow, okay? If the point in space is closer to the electric charge, then it means that the electric field is going to be stronger, right? But doing that for the whole space is too much work, okay? So instead of keep on drawing arrows all over the place throughout the whole two-dimensional space, we have another notation that we call the electric field lines. Okay, here you go. Here's another representation of the electric field. We can either represent the electric field in terms of vectors, electric field vectors, or electric field lines. For a point charge, the electric field is just those lines moving away from the central charge, okay, in a radial direction. And what else can you tell me? Okay, very important. In the case of the vector notation, the stronger the electric field, the longer the length of the arrow, right? Here, you know, the strength of the electric field is not denoted by the length of the arrow, but is denoted by the closeness between electric field lines, okay? Notice here that those two lines are closer here than they are close than here, right? The distance here there is further away from the distance here. What does it mean? It means that in this region, the electric field is stronger than in this region here. Make sense? Okay, so let's write it down. Two different ways of representing the electric field. I'm going to erase that. Okay. There are two different ways of representing the electric field. Graphical ways, right? Let's put it this way, graphical, because you can also represent it in a mathematical way. There are two different graphical ways of representing an electric field. By drawing a vector, by one, drawing a vector, the longer the vector, the stronger the electric field is. and 2 by drawing an electric field line. Electric field line. The closer these lines are, the more intense, the stronger, right? The stronger the electric field is. That 4-point charges is very easy to draw those electric field lines. They're just in the radial direction. Here we have the electric field of a negative point charge. If you were to repeat, the electric force between this charge and a test charge that's positive, the electric force would be towards the center of this guy, right? So you'd have a representation like that. Okay, so here you go. Here again, the representation in terms of electric field vectors. Things start to become complicated when you have not just one charge, but you have 2, 3, 4 charges, and so on. Okay, so let's see. Here you go. We have an x and y axis, right? We have this little charge Q at the position minus A. This charge is positive, and you have another charge at position plus A, which, by the way, is also positive. Both of them are positive. Okay. If Q here is positive and I'm denoting this charge as being Q, it means that it's also positive, okay? And now we can start playing with the electric field, with the configuration of the electric field of an ensemble of charges. So here you go. We start with the first charge. Let's see how the electric field, just in a qualitative fashion, right? Charge here is equal to this charge, and I want to find out what's the electric field at this point here. It's a kind of a middle point. The distance from here to here is the same as the distance from here to here, right? So how do we do that? We go ahead, we recognize that this is a positive charge. Consequently, the electric field is away from the charge. Positive charges, we say they are sources of electric field. Right? And I wrote down E left charge. I meant the left charge. And then we do the same with the electric field of this other charge. Should be pointing to the other side. Because there is symmetry in this problem, the intensity of this field is the same as the intensity of this field. Similarly, the angle between this charge here and this axis is the same as the angle between the electric field of this other charge. Because the angle is the same and their intensity is the same, the horizontal component of the net electric field cancels out. Make sense? And we end up with a net electric field equal to what you see right here. Let's see if it is drawn in scale. Let's see if it's drawn to scale. No, yeah, it is kind of, right? Right? It is drawn to scale. That's a very good way of having a qualitative idea how the electric field behaves for a set of charge distribution. Okay, so here you go. That's the net electric field. Oh yeah, okay. What about here at this spot? Not at this spot along the axis, but at this spot right in here, a distance A from the y-axis, and just above this charge. How does the electric field look like? Okay, this one is a little bit more complicated than the other one. Because now, why is that complicated? Because this distance here is less than the distance of this charge here, okay? So when we perform our qualitative analysis of what the electric field is going to be, remember those two charges has the same magnitude, Q, right? But because the distance of this charge is longer, it means that's going to have an electric field that's weaker than this one, right? So here you go. That's exactly what I drew, right? Radial direction, see that? Radial direction. So, and then all you have to do now is to combine those two electric field vectors into a net electric field, which is this one here. Note, see the difference now. In this specific case, we do not have a symmetry between those two charges. Right here, we have a symmetry distribution between those two charges. That's why we get just a component along the y-axis. Here, we have a combination of x and y-axis components for the net field. Okay, let's see. We could do also for, let's do one more. Let's do one more. I did only two electric fields here. I want to do a second, third field. Let's see here. Now, I don't need that. I did too much. Oh, here you go. Now I want to know, I'm going to give you a simpler problem right now. What's going to be the electric field at this spot here, right? What's going to be the electric field at this spot? Can you picture that yourself? Okay, so I'm going to have an electric field contribution of the left charge. I'm running out of space here. So let me, it's going to be something like that. Okay, so let's see, I'm going to do this. Yeah, I'm going to do this one here instead. Instead of a red arrow, I'm going to do that little blue arrow to want to know the electric field at this spot, but it becomes kind of invisible, right? Let's see if I can make it a little bit thicker. Got the idea? That's the electric field of the left charge. And then this charge will also have an electric field in the same direction, pointing to the left, with one important difference. It's going to be shorter because it's further away from the other charge, right? So if this one here below is the electric field of the left charge, this other one is going to be of the electric field of the right charge, right? When you sum those two vectors, which by the way are pointing in the same direction, we end up having a net electric field that's longer because I didn't plan properly. Now my field ended up going outside my slide, right? Make sense? And so on. We can repeat that for a different charge distribution. And I'm gonna put it red color to keep consistent, right? What would be a different charge distribution? Okay, it's gonna be x and y axis. Now the charge is one charge is gonna be negative and the other positive. This charge distribution that you see here is very important. It's called the dipole. It's called a dipole, two poles, one positive, another negative. Okay, let's see how it looks like. The electric field looks like. Let's repeat that, right? Here you go. Along the y-axis, one point along the y-axis, the electric field due to, hey, wait a minute. I made a mistake here. the electric field due to the right charge is going to be in this direction. Why did I put there? I don't know. Okay, so here you go. Make sense? That's going to be the direction of the electric field of the right charge. The electric field of the left charge is going to be upwards. Okay, now I have it right. So let me just erase this guy here. I don't need that. Okay. The electric field of the positive charge, the charge that's to the left. Why did I put right here? Let me erase it. Is going to be in this direction. The electric field of the negative charge, that's going to be the left charge, is going to be in this direction. Because the distance of this charge to this point is the same as the distance of this charge to this point, it means that the length of those two fields are the same. Also, because this triangle is similar to this triangle, this angle here is going to be theta, and this other angle is also going to be theta. This angle here is also going to be theta, okay? Because those two angles are the same, right? Because those two angles are the same. What does it mean? It means that the y component cancels out and the net electric field ends up being in the horizontal, right? We can do for distance further away, the axis, and at other points as well. Okay, so here you go. Remember, this is the electric dipole. Okay, so let us write down now the electric field in the same way that we wrote the force, right? In terms of equations, mathematical equations. 10:45. Any questions so far? Before we move in. Okay, let's do a simple example here. Okay. Consider an electric dipole along along the x-axis. The positive charge is at x equal to minus a, and the negative charge is at x equal to plus a. The positive charge, both charges have the same magnitude q, right? Find an equation for the electric field along the y-axis in terms of r, the distance between this distance. Let's see. In terms of y and a. Okay. In terms of y, there are y coordinate and the a value. Okay. Let's do that together. Solution. Just like the force, the electric field, obeys what we call the superposition principle. And what does it mean? Let me get, here you go, I'll get this one here. Electric field, the net electric field is equal to electric field. I'm not gonna make it E1. Instead of, I'm gonna say electric field of the positive charge plus the electric field of the negative charge. Right? Make sense? We're gonna add those two vectorially. The electric field of the positive charge can be written down in terms of K, Q over, I'm gonna write down R squared, okay? But it's not just R squared, it's R, it's R of the positive charge, right? Like that. And we still have the unit vector along the positive charge, okay? Which is gonna be different than the other unit vector, by the way. So we can have the same thing for the other charge. That's the notation we are using here. Here you go. Makes sense? We can change, we can denote, we can here write those unit vectors in terms of x hat and y hat. There is a way to do that. And we're going to do that right now, okay? But first, let us recognize that what you see right here is what? It's going to be y plus y plus, let's go back here to our drawing, right? That's r plus, right? Here is a, here is y. So r plus is going to be square root of y squared plus a squared. Make sense? Y squared plus a squared. R is going to be that, y square root, right? But because we're squaring the r plus, the square root disappears here. The same thing can be said about the other r minus. Right angle triangles, right? So they have the same denominator. Oh, and by the way, there's something that I'm missing here. What am I missing? You know, don't forget, this is a negative charge. So I gotta put a parenthesis here for this Q, right? This is a negative charge. And since I went the next step, I can put a negative sign here as well, because this negative side can go to the other side. That's the net electric field. Now, how do you write those two here? Okay, you write those two here by looking at the drawing. Let's see here. Okay. So here we have a theta angle, right? Here we have a theta angle. And here we also have a theta angle. Okay, tangent of theta is going to be y divided by a, right? Okay. But the tangent of theta is not the right one. It's not the most convenient one to use. There's a better one. Before we get into that, you know, let's go ahead and illustrate my theta angle here. Here you go. Here you go. Okay, here you go, theta. E net, right? I want to put the E net right in here. And then, thank you. So I'm gonna need another. I'm gonna denote here theta. It is lowercase q. I'll change the font to symbol. Good. And we get that. And I don't need the rest, right? Okay, so the x component of this electric field is going to be, you know, this arrow sine of theta, right? But we want to write down the r hat, the r hat plus in there. The r hat plus that we have right here, let's write that down separately so you can understand better. It's going to be what? The magnitude of r hat plus, here you go, magnitude of r hat plus times what? Cosine of theta, right? Times magnitude, put it here, you go. Cosine of theta in the x direction plus, you go, magnitude of r hat plus sine of theta in the y direction. They're both positive direction, right? It's to the right and upwards. That's not the same we can say about the negative, r hat minus. R hat minus is different. Here you go. R hat minus cosine of theta, yes, because this angle is the same. But along the y direction, it's going to be negative, right? Because it's pointing downwards. Okay, that's how we solve this problem. Oh, there is one more thing that we can do. Magnitude of a unit vector is going to be what? It's going to be 1, right? It's going to be 1. I'm going to put 1 here, and then I'm going to erase it because it becomes redundant, right? I'm going to erase it. We don't need that. We don't need that. And we don't need that. And then there is one more thing that we can do. We can here write the cosine and sines in terms of our non-parameters, y, a. Okay? Let's take a look here. Okay? This angle here is equal to this angle here. Okay? So here you go. Right? Oh. Right here. Make sense? I'm going to draw a line there for you to see it. Those are similar triangles. We get that from geometry. Oh gosh. My mouse is, let's see here. Okay, good, I got it. That's it. So the cosine of theta now can be a divided by this value here, right? Make sense? Oh, it's all geometry. Now here you go. A divided by r plus, right? But r plus is what? Okay. A divided by r plus. Yeah, that's cosine of theta. And sine of theta is going to be what? Y divided by r plus as well. But r plus, you know, can be here written as, here you go, no, square root. I'm gonna put that y squared plus a squared, and we gotta put a square root here. We're gonna go on a break very soon. Here you go. Okay. And we have the same for the other one, right? The only difference is going to be the negative sign. And finally, we can have our net electric field. Our net electric field is going to be R plus. Here you go. Hopefully I didn't make any mistake here. That's the R plus. And that's the R minus hat. And don't forget, we have to have let's see here. Let's do it again. Here you go. We got it. And then gonna put my parentheses here and parentheses here. Okay. Can we do more than that? 10:58. We're gonna go in a break very soon. Okay. Remember, we're doing just for along the y-axis, right? So let's see what we can simplify. Can we simplify something? It looks like we can. This term here is exactly the same as this term, which combines with this term in the x direction. And this term too is the x direction, with the difference that we have a minus sign. See that? With the difference that we have a minus sign. So this term here cancels out. Those two terms here cancels out. So I'm going to cancel this with this one. Okay? However, those two terms here, they sum up. They sum up with each other. So we end up having something like that, 2kq multiplied by that. And this minus sign cancels out with this other minus sign, and you end up summing up. Okay? So that's what we get for the net electric field of a dipole along the y direction only. Okay? 10:59 right now. Remember this, we took quite some time to do. Let me see if I got it right. I'm getting along the y-axis. It looks like I made a mistake here. Let's see. It looks like I made a mistake because you're supposed to get along the x-axis. Help me out here. Let's see. Minus. Okay. Let's see. I have to substitute here. Yeah, let's see what I did wrong here. Anybody see anything wrong here? Yeah, it's not the x-axis. Oh, that should cancel out. What a shame. Let's see. R plus. Yeah. Yeah, it's minus the y. Let's see. Minus plus. Yeah, I do not know what I made. Let's see here. Away towards this. Okay, let's have our break, and I'll figure out what was the problem here. We're supposed to, according to the drawing, we're supposed to get an x hat result here, but I'm getting a y hat. Okay, there might be a problem in the sign. Okay, in the next 15 minutes, I'll figure out where is the problem, and I'll let you know. Okay, any questions? Unless you know where I made a mistake here. Okay. If you don't, let's meet again in 15 minutes. Break till 11:15 a.m. And I see you in 15 minutes again. Resume. Okay, so we are back here. Let's go back to the syllabus, right? Here you go. I'm scheduling a quiz for the next Monday, so make sure you're here. It's gonna be the last 20 minutes of the class, like we did before last semester, right? Now, what's the problem here in this in the equation that I derived? The problem lies right in here. Okay. Why is that? Okay. the r hat minus vector is already telling you the direction of the electric field, okay? That's where the problem is. Once you spell that out here, you cannot put a minus q here, okay? The proper way of writing down this equation is like that, you know, so you don't incur in the same mistake that I incurred. It's like that. Here you go. You write down the magnitude of the electric field times the direction of the electric field. Then you write down the magnitude of the other electric field, right? Which, by the way, is the same direction as the other one. And the r hat minus. That's the proper way of doing that. And now that we have done that, here you go. We have a plus sign here. That's the magnitude of the electric field. Magnitude of the electric field, they're the same because the distance is the same. Here is correct, no problem here. So the problem was right here. And once we get that, you know, the negative, the y hat cancels out, right? And we end up with something like that, with x hat here. Okay, so remember that. Now let's take a look at our. Any questions about that? Is that clear? What's happening here? Wiley plus. I'm gonna log in. Physics 7, right? We still have homework 1 in there. Let's see. Let's take a look at the book. Lunch. Okay, so Coulomb's law. We covered Coulomb's law, and here are some examples, some example numeric examples. Notice that this problem, this example here is more difficult than the other one, right? Here you go, that I did in class. The more generic problem with numerical values. What else? Let's take a look here. Chapter 1, chapter 21 we're doing, right? No, chapter 18. Okay. Origin of electricity, charged object and electric force, conductors and insulators. I don't think I cover conductors and insulators, right? Did you cover? Yeah, the quiz is during class. That's right, Randy. The last few minutes. The quiz is during class. You know, come by and the last 20 minutes of the quiz of the class. And conductors and insulators. Let me give you a little word about conductors and insulators. Okay, we covered the electric fields, electric field lines. Okay, and then we still have those two topics. Let me tell you about conductors and insulators. Let me make sure I didn't cover that for you first. Conductor. Let's go conductor. Oh yeah, we did cover. Okay, we did cover. So just remember that the electric conductors are materials that let charge to move freely, and electrical insulators, charge don't move freely. So I don't have to cover that. I already did. And
Professor?
oh yes.
Will the quiz be based off of your lecture or the book or both?
Both. Mm-hmm.
Okay.
Okay, it's gonna be very simple.
Thank you.
Right? And mostly what I cover in the classroom. And let's see. Electric field lines, we did that. Let's take a look at Gauss's law. Okay. Okay, so we're going to skip that, okay? Let's talk about Gauss's law.
And Professor, next Monday is President's Day, so do we still have class?
Let's see, let me check.
Okay, thank you.
I thought that it was on Thursday, wasn't that? Let me check. If it's a holiday, we are not going to have class. So let's see here. Just, you know, we're doing what, 3 to 5 questions, right? We're doing 3 to 5 questions, so expect something like that. 3 to 5 questions for the quiz. Okay, let's see one. Holidays, right? Let's take a look here. Holiday, present days, it's a Friday. Let me see, Friday through Monday. Oh, okay, so Monday is a holiday, right? Okay, so we cannot have a quiz on Monday. Thank you for reminding me. I saw this when I was doing my schedule, I saw this. Let's see, I saw this one, but I didn't see the other. Okay, so let me update my syllabus. Thank you for pointing that out. And
Yes, sir.
yeah, so let's see here. I'll have to fix that. Insert rows above. Nope, it's not what I want. Insert cells above. So, okay, so here we go. And I have to fix this one now. That's insert cells. Good. There's gonna be a holiday. Oh no, not this one. This one here. I mean, now I have to. Okay, so here you go. So we leave the quiz for the other Monday, and here is going to be not applicable. Holiday, President's Day. Okay. And now that's going to be lab here. Lab here. This one is going to be an exam. Let's see, I want black. Okay. Another lab here. Another lab here. Well, I will fix that my spare time, okay, and then I'll post there. Things starting to become a little bit complicated here. Wednesday, yeah. Let's see. Okay, this one is supposed to be spring break, right? Monday, and okay, good. So I can make it. This one is spring break. Yeah. Wednesday. And Monday, holiday, Memorial Day. Okay. And that's going to be this one here. Gonna be something like that. Hopefully I didn't make any mistakes. President's Day, Monday. So let's leave the quiz for the other Monday. Okay, next. Wednesday is gonna be electric field 1. Okay. Here you go. And now we can start talking about Gauss's law. Okay, so what's Gauss's law? Gauss's law is just a different and more convenient format of Coulomb's law. Okay, that's what Gauss's law is all about. Gauss's law is Coulomb's law in a different format. Okay, and because of this format, it becomes easier for us to, using Gauss's law, it's possible to solve, to determine the electric field of charge configurations of different charge, not everyone, but of a few charge configurations in a easier fashion if compared with Coulomb's law. Okay, that's what it's all about, Coulomb's law. So what do you have to memorize for Gauss's law? Okay, how to memorize it? Memorize it. Okay, how to memorize it? Let's see if I have a drawing here for you. Here, we don't want to look into that. Not every geometrical configuration can be used to find the electric field using Gauss's law, okay? See here. Okay, here you go. One more important thing, another important thing. Gauss's law is capable of solving only certain problems that involve symmetry. Okay? and I'm gonna line up which problems are those. Okay. First one, first one and simplest of all is that of a point charge. Okay. How do we use Gauss's law in this case? Here you go. Here's the case of a point charge. In the case of a point charge, suppose that you didn't know Coulomb's law for a point charge. Suppose you didn't know that the electric field was KQ divided by R squared, right? All you had to do was to remember that, for instance, a point charge, a positive point charge, is the source of electric fields. Okay? And because this is a point, this point has some symmetry, some geometrical symmetry. Okay, so because it's a source for the electric field, it's very reasonable to assume that the electric field here at this point, that is a given distance from the point, would be the magnitude of the electric field at this point would be the same as the magnitude of the electric field at this point, the magnitude of the electric field at this point, and so on. Okay, the only difference would be that the direction of the electric field would vary. Okay, having said that, we can say that we can create a geometrical surface around this point charge that has symmetry. And this geometric surface would be what? This geometric surface would be a sphere surrounding the electric charge. Okay? Oops. Let's do that again. Here you go. So, because all those points of the sphere are the same distance from the point charge, we can state that the electric magnitude of the electric field here is the same as the magnitude of the electric field here, and so on. Okay? That without knowing Coulomb's law. And then what else do we do? You establish what we call the area vector, the direction of your area vector along this surface. Okay, the area vector always points away from the center of the surface, from the center of curvature of the surface. Okay, this is a curvature of the surface. The center of the surface is somewhere around here, so the area vector is pointing away. And then we use Gauss's law. Okay. For the case of a point charge, Gauss's law would be written like the following. E times A is equal to the charge enclosed divided by a constant that we call epsilon naught. I want to talk a little bit more about this constant. This constant is related to, by the way, to that other constant that we saw. I'm going to write it in terms of the K constant, okay? 4 pi K. That's what epsilon naught, that's the relation between epsilon naught and the K constant. Okay. This term that you see right in here has an interpretation. The term on the left side has a physical interpretation. And it is called the electric flux. Okay. But I'm going to go even further. I'm going to be even more specific about this formula, okay? For a point charge, it ends up being equal to that, okay? But to be more generic, in reality, the electric flux is going to be EA times the cosine of the angle. And I'm going to put that, I'm going to use the same angle of the book, phi. Whereas this angle phi, what's this angle phi? Is the angle between the electric field and the area vector. For the case of a point charge, this angle is always going to be 0, okay? So that's the Coulomb's law in a different format. Coulomb's law in a different format. So let's do that. We're doing that assuming that we do not know Coulomb's law. Okay. If I were to write this equation, okay, how would he write it in the following way? Yeah. Here you go. That's the electric flux. All this term here is called the electric flux, right? Equal to Q enclosed. What's Q enclosed? I'm going to tell you very soon what Q enclosed is. Okay. Electric flux. So what's Q enclosed? Okay. Q enclosed is how much is the charge inside this surface? This surface here we call the Gaussian surface. For different charge distributions, you know, we may have different appropriate Gaussian surfaces. So think about a sphere, right? A sphere around, imaginary sphere around your charge. Okay, we're going to do a bunch of problems so you become more clear what surfaces you have to choose for different charge distributions. Okay, so here you go. For the case of the point charge, this angle here, phi, is going to be 0 because the electric field and the area vectors, they point in the same direction, okay? So here you go. I'll get cosine of 0 is 1, right? I'm going to use the other formula that's more familiar to you. In this case, the Q enclosed is going to be the charge Q. Okay. And then we solve for E. Okay. By solving for E, I mean I have to pass the area to the other side. When I pass the area to the other side, don't forget this is the area of the Gaussian surface where, here you go, where A is the area of the imaginary Gaussian surface. Whereas this surface is a distance r from the center of the charge. Okay. What would be the area of this sphere? The area of the sphere, you know, it would be 4 pi r squared. Okay. And when you do the math, you find out that the electric field of a point charge using the Gauss law coincides with the electric field of a point charge using the Coulomb's law. Okay. So I would say that Coulomb's law is just a special case of Gauss's law. And we can do the same for other types of charge configurations. So we did for a point charge. The next one that you should know is next. Next, we will use Gauss's law to find the electric field of a charged thin spherical shell. Again, we have the case find the electric field of uniformly charged charged. I'm not gonna put C in the spherical shell. Uniformly charged and very thin. Let's put it this way: spherical shell. So I'm gonna show you another case. So here you go. Oh yeah, here you go. Do you see that? That's how we do that's how we solve for the point charge. I already did that, right? You have a point charge here, charge Q, X and Y direction, axis. We know that the electric field moves away from the electric charge. Okay, we just don't know the magnitude of the electric field because the positive charges are sources of electric field. And then because of the symmetry of this problem, we can draw a spherical surface, imaginary surface around the charge. Okay, that's what this circle is all about. Okay, and okay, notice that the area vector of this spherical surface is away from the surface itself, and it makes an angle of 0 degrees with the electric field. Okay, here you go. Here's the infinitesimal area vector A. Okay, that's the radius of the spherical, the Gaussian spherical surface. And then we go ahead and solve the problem the way it did. Okay, and now what we're going to do? We are going to solve the electric field for a spherical shell that's very thin. Let's see, the spherical shell. No, this is not the spherical shell. That's the spherical shell. Here you go. Let's do the spherical shell. That's very thin. It has a charge distribution. It's positively charged. And we do exactly the same procedure that we did there before. Okay, the first thing is we do know, here you go, that this spherical shell has a radius R. Let me write that down there, right? Here you go. Spherical shell of radius R, and charge Q. Okay. We go ahead and put our X and Y axis, and this charge is uniformly distributed throughout this shell. Consequently, this charge distribution has some geometrical symmetry. The geometry, consequently, the Gaussian surface that most useful for this case is going to be a sphere, whether it's inside the spherical shell or outside the spherical shell. Okay, so let's start calculating the electric field inside this spherical shell of radius R. Okay, don't forget that we still have the electric field outside the spherical shell as well. But let's calculate the electric field inside the spherical shell first. Okay. Going back here, we have, you know, we are going to get this formula, which is the electric flux. I'm going to get out here, take this one out. Notice that inside this spherical surface, to enclose means the electric charge that's inside this Gaussian surface. Okay, notice that there is no charge inside this Gaussian surface. Because of that, what we have here on the right side is going to be our 0. Okay, the area of your Gaussian surface is not 0. And the cosine may not be 0 as well. So what we have this situation in which, and by the way, I'm going to put here inside, okay, inside. So the only term that's going to be equal to 0 in this case must be the electric field. So what we conclude? We conclude that for a electrical shell, for the electric field inside an electrical shell is going to be 0. Okay. Next, we will use Gauss upon the electric field in front of start solution. Start with R less than big R. Okay. Inside the shell, the spherical shell. Now we're going to do outside. Now let's do outside. Now let us do outside the shell. Or greater than big R outside the spherical shell. So we go back to my drawing here. Very important. Okay, so we discovered that inside this spherical shell, the electric field is 0. Now we're going to do outside. Because of the symmetry of this shell, we can realize that the electric fields are going to point away from the surface. Because we have a uniform charge distribution, those electric fields are going to be perpendicular, normal to the surface. Just like the case for the point charge. Okay? Because our Gaussian surface is also spherical, we are going to have an area vector that's going to be parallel to those electric fields. And we have a situation similar to that of a point charge. Okay? So let us solve this problem. So the problem outside the shell. One, due to the symmetry, since the shell has spherical symmetry, and the charges are uniformly distributed, a convenient Gaussian surface would be that of a sphere as well, of radius r, lowercase r, to distinguish from the uppercase r. Okay? Applying Gauss's law, we have, here you go, this one here again, but now is going to be outside, okay? Outside the spherical shell. We don't need that anymore. The angle between the area vector and the electric field is going to be 0. Consequently, the cosine is going to be 1. And now we have the charge enclosed by my Gaussian surface is going to be big Q. We have 7 more minutes to go. And then we get exactly the same result that we got for the point charge. Here, we're going to have A here. The area of a sphere is going to be 4 pi r squared. 4 pi cancels out with 4 pi. And we do get the same result for a point charge. Okay. Here you go. In conclusion, the electric field for a spherical shell is the following. How do you write that down? Write that down the following way. You go E equal to here you go. That's the one I want. E is gonna be equal to 0. Oops, 0. For R less than big R. I need a little bit more of space here, right? And E is going to be equal to KQ divided by R squared for R greater than big R. Actually, it's R greater or equal. Here you go. Okay. That's for a spherical shell. What time is that? 11:55. Okay, let's try to do one more. 5 minutes. Hopefully you can do it. That's going to be, let's see. Let's see if we can do that. You know what? Let's stop now. And any questions about that? We're going to. So remember Gauss's law, okay? It's given by this equation right here. EA cosine of phi, where phi is the angle between the electric field and the area vector. And what's on the right side is K for pi K, Q enclosed is how many charges are enclosed by the surface, by the Gaussian surface. So what we're going to do next time, we're going to do calculate the electric field, the E field for a large planar charged surface, uniform distribution. Okay, that's spelled out in the book. Okay, one of the examples there, and then I will see you next time, right? Any questions? 11:57 now, 3 more minutes to go. I have office hours right now. If you want to stay around and chat a little bit or ask any questions, I'll be available. Okay. So see you at the office hours or next time on Wednesday if you don't stay around. Thank you.
Thank you, Professor. Have a good day.
You too.